So we just did a principal components analysis. We reached this conclusion, but our factors are not rotated, right? So we're going to go back and we are going to do the same sort of analysis. We're going to go dimension reduction, factor, same items. Descriptives is not going to change. We're going to leave all of that. Extraction is not going to change yet. We're going to leave all of this. Oh, actually, you know what? Yeah, we're going to leave unrotated. We're going to leave scree plot. We're going to leave it as principal components for right now. Rotation, though, we want to change. So we're going to select Varimax. It's going to give us a rotated solution and our loading plots for the rotated solution. We don't need to worry about maximum iterations for convergence. It should converge well before 25. We will roll with this. Now, Varimax, I said, is what type of rotation? It's orthogonal, correct. Didn't I click that? Scores, we're going to keep the same. None of that changes. Options, that will stay the same as well. So we only changed one thing here, right? And what was the one thing that we changed? Rotation. So when we change that and we select rotation, this will not change. Notice we still have ones here. Our correlation table stays exactly the same. Our initial extraction will also stay exactly the same, as will the communalities because we're doing principal components, right? This looks a little bit different now, right? Now, we're still going to account for the exact same amount of variance. You're not going to change the amount of variance that gets accounted for, right? But the amount of variance that gets accounted for by factor changes pretty dramatically. So in the first factor, initially, right, unrotated, we have an eigenvalue of 15, and it accounts for 26% of the variance. Once we rotate that factor, our eigenvalue drops, and it only accounts for 18% of the variance. Notice here, we also get much higher eigenvalues for this initial factor. And since we stopped at an eigenvalue of 1, we don't actually get eigenvalues after our rotated factor. Let's do something. Let's go analyze. We'll come back. I mean, don't worry about it. I'm just going to change one small thing. Instead of eigenvalue of 1, let's do eigenvalue of 0.5. That will allow us to take a look at what the next highest eigenvalue is in our rotated factors. So you can see before, right, we stopped here, right? We had an eigenvalue, and then the next one was 0.959. However, with our rotated factors, we wind up getting eigenvalues that stretch way down here when we switch it to an eigenvalue of 1, right? Or I mean, when we allow an eigenvalue of 1. When we say we're going to stop at an eigenvalue of 1, it will stop that based on unrotated factors, not on rotated factors, right? And so consequently, we wind up with a rotation factor of eigenvalues that stretch all the way down to 15, and it's very hard to say that there's a difference between 15 and 16 here, right? The stopping should occur on your unrotated eigenfactors, not on your rotated eigenfactors, right? All right, let's keep looking down here. I might have to go back and change this again, but anyway, here is our scree plot. We have 1, 2, 3, 4, 5, and again, I would say that 5 is roughly the knee here. You could also say 6 is the knee, I suppose, but I would probably go with 5. And the rest of these are, well, unfortunately, I selected that eigenfactor of 9. Let's go back and change that, or of 0.5, because it makes it gives us way too many factor scores. Change that back to 1. We're going to jump past our scree, and here's our component matrix. And so notice here this first one loads on factor 3, but also on 5 and 6, just like it did before, right? Now when we look at a rotated component matrix, it makes a big difference, right? That first item no longer loads on factor 3, it loads on factor 2, and it loads almost not at all on any of these other factors. Negatively on factor 6, so I have a reserved and cautious attitude towards life, and factor 6 winds up being, I generally seek new and exciting things. So we did see that negative before on that factor, right? I'll try anything once. What does this sound like as I'm reading these? I try new and exciting things. I'll try anything once. What type of person is this? I quite enjoy taking risks. Thrill-seeking, sensation-seeking type of person, right? Yeah, of course. And I would enjoy parachute jumping. That doesn't actually load on our same factor, right? Now we know that it should load on that factor, but it doesn't.
It's a real item, like the realistic real, like enjoy parachute jumping.
Yeah, I would enjoy parachute jumping. Yeah, that's a real item. So anyway, all right. Let's keep scrolling down here. Component transformation matrix, you don't need to worry about. Component plots in space. Again, this actually is important if you only have 3 components, or especially if you only have 2 components. And this isn't rotated, but when you have, you know, what we're finding here, which is 5, 6, 7, 8, 9 components with 56 items, it just is too messy to make any sense out of. Component score coefficient matrix, and this is unstandardized component coefficient matrix, and then component score covariance matrix. Again, not going to worry about that. So what is the problem here now? There's still an issue, right? And what is the issue here?
Too many factors.
Too many factors, and we have a ton of variance, right? We're assuming that all of this error variance has some sort of meaning, and it doesn't. It clearly doesn't, because we're only able to account for, even with all of the factors that we've got, 56% of the variance, right? And so what we're going to do now is we're going to say, theoretically, we're not interested in error. We want to know how well these factors tap in directly to how well these items tap in directly to the factors that we're trying to assess. And to do so, we have to change something. And what is that something that we have to change? Say that again? Yeah, right. We have to change this from principal components to factor analysis. So let's make this switch. Almost always, I have never once done principal components. I'll just throw that out there.
What's the difference?
The difference is that principal components assumes that you have got error, and that error is somehow important. Factor analysis is saying we're not going to worry about error. We're just going to focus on the extent to which each of these items is related to the factor. And when you do that, what happens? You remove variance, assuming all of the variance, and you only focus on shared variance, which means you wind up getting better loadings on each factor, right? Your factor loadings will increase, and you wind up having more discrete factors, right? Less error in your models in general. So descriptives, coefficients, we will leave all that the same. Extraction, oh shoot, you know what? I don't want to change that just yet. I want to do one other thing. Rotation. We assumed that these things are all uncorrelated, right? But let's now assume that they are correlated. Kappa is the extent to which it allows them to correlate, and 4 corresponds to anything less than 90 degrees, right? Because you have 4 quadrants. So we are going to leave everything the same, but now do correlated factors. This component score thing will change because now it's going to say, well, let's just scroll down. So extraction, these things, your extraction winds up being the same. Your initial communalities or initial amount of variance is the same. Did I change something else? Oh, no. Nope, this is right. Now we allow those things to correlate. This is an oblique rotation. Yeah. And so when you select an oblique rotation, we wind up getting rotation sums of squares loadings, which is the same as, roughly the same as eigenvalues for unrotated, right? But instead of eigenvalues, since it's allowing for an oblique rotation, you get what's called rotation sums of squares loadings. Scree plot, 1, 2, 3, 4, 5, looks roughly the same. But notice we're not getting any different numbers of factors, right? We're still getting like roughly the same amount of factors, though this is a much higher number than we're getting over here, right? The amount of variance accounted for, though, it's always going to stay the same. It doesn't matter if you're doing rotation or oblique or orthogonal.
So do we guide ourselves with the sum of square loading or with the eigenvalues?
With this, you still are going to do your selection based on sum of squares, or I mean, based on original eigenvalues. Yeah. Because you always use the unrotated eigenvalues as your guide for how many factors that you should select. All right.
I have a question.
Shoot.
So you said that the reason why we're going to change the analysis approach to factor analysis now is that there are still too many factors and a lot of variance.
We haven't actually changed it just yet, though. Go ahead.
But this is why we're going to change it.
Yes.
Right?
Yep.
Can you tell us more about like what makes this too many factors? And,
Yeah, so I mean, if you're doing exploratory factor analysis, it's impossible to decide what really makes something too many factors, right? In this case, I know that it's too many factors, but I think it's unfortunate because next week it's going to be easier to explain that when we're doing structural equation modeling, because you can actually compare these number of factors and determine what's better or worse as far as numbers. But in this instance, we scroll back up here. If you wind up having a number of factors that are in the ones, then I think you wind up starting to say like there's just too many factors that aren't accounting for a lot of variance, or each accounting for like one item level of variance. And so that's what we're seeing here, right? We're seeing like a whole ton, well, half are only accounting for one item level of variance. And so if you have a bunch in ones, then I think that's a good indication. Like I said, unfortunately, there's no real test in OLS factor analysis to say like, well, it should be this versus that. But it does indicate that you've got a lot of factors that aren't accounting for a lot of variance, right?
so we could possibly do better.
Yes, yeah, you could possibly do better. So, all right, and then finally, this covariance matrix is actually telling you, what did it look like before? Do you guys remember when we had?
Just zeros.
It was ones and zeros. And so ones and zeros means that none of those factors are allowed to covary at all, right? And in this case, we're saying, nope, we're allowing all of these factors to covary, and this is the extent to which each one of them covaries. That's how you know that this is an oblique rotation and not an orthogonal rotation, right? All right. Finally, we're going to do this the way that it should be done, and that is using, principal access factoring. Principal access factoring is traditional factor analysis. And it's only going to allow us to look at the variance that is shared across all items, right? That can be accounted for. And it is can be accounted for by every single possible factor. But nothing. I don't know why I said but. All right, correlation matrix. Actually, whoops. Correlation matrix is exactly the same, right? But communalities are different. And so I had said that almost always your extraction should be less than your initial, but in factor analysis, they should be very, very close, right? It's not quite perfect here, right? So we see like 0.3, 0.28, 0.44, 0.436, and then we see this weird one, 0.39, and the extraction is actually accounting for 0.418 amount of variance. How are we accounting for 0.418 amount of 0.39 variance? You want to take a guess at this?
Pulling from another item.
No, I mean, so technically this is with the extent to which this item overlaps with every other single factor out there, right? And it winds up just being a mathematical anomaly. When you account for more variance than what's there, that means that you have negative explained variance. And what is that called? I said this term last semester once, I think. You should all remember it. It's an anomaly that just happens with factor analysis, and it's called a Haywood, right? A Haywood case. And so you see these every once in a while. You see a negative residual variance, and that is that you're explaining more variance than what can be accounted for in the model. There are some ways that you can go in and look and try and understand what's going on with a Haywood case, but for the most part, it's a mathematical anomaly that happens, right? And it's because statistics aren't exact, and so you wind up with this weird stuff once in a while. SPSS won't give you an error message if you have a Haywood case. M+ will, but it won't tell you that you have a Haywood case. It'll say something wrong with this. We have negative residual variance or something along those lines, right? But residual variance is what? Unexplained, right? And so negative residual variance would mean, like if you have zero residual variance, that means all of the variance is explained. Negative residual variance means, hey, you actually have explained more variance than what there is to be explained, right? And that's what a Haywood case is. And so you see that every once in a while. And we will definitely see it next week when we do it in M+. And there are ways, the nice thing about doing it in M+ is you can go back and say, like, no, the variance is actually exactly this. And you can fix the variance so that it can never explain more than that negative, or more than the max amount of variance. And we'll do that next week. So, all right, so there are our kind of communalities. And now we get this. We get our initial eigenvalues that go all the way down to 1, and this should look exactly like it's always looked in the past, right? But when we switch to our oblique rotation, we get something a little bit different. And now this, in factor analysis, is different from principal components analysis in that since you're not accounting for or starting with 1% of the variance, you can't follow the initial unrotated eigenvalues. You have to follow your rotated eigenvalues. And so for factor analysis, you follow the rotated eigenvalues instead, and that shows how many factors here. Remember, in principal components analysis, your unrotated and rotated eigenvalues are exactly the same anyway. In factor analysis, they're not. What do we get here? How many factors?
5.
And are there 5 clear factors? I would say it's pretty clear, right? That last eigenvalue is 0.76. That is much different than our last eigenvalue before, which was how much? 0.96, right? So this is suggesting a much clearer cutoff for our factors. Let's scroll down and let's have a look at our scree plot. 1, 2, 3, 4, 5. I feel like the knee is much more defined. Before we were saying the knee would be 5 or 6. Here I feel like the knee would be 4 or 5, possibly 6, but I feel like 5 seems like a much more defined spot. Here's our factor matrix. We see that for this item, factor 3, but also 5, 6. Let's scroll down to our rotated factor matrix. And for our rotated factor matrix, we get, is this the rotated one? Yes. Is this rotated? I don't think it is. You can check if it's the rotated matrix by coming down here. It is the rotated matrix, right? Yeah. So anyway, this item winds up moving over to here. I mean, this is still not all that great, right? This item winds up actually loading on a couple of different spots. The highest loading is right here. You can do, let's do this quick, a way to try and reduce this a little bit further, or at least make it a little bit more clear, is you can say, oops, not in here. Is it in options? Yes. We're going to say that if a factor loading isn't at least 3, and this is a common approach to say factor loadings of at least 3, if a factor loading isn't at least 3, then we don't want it to be included in our factor matrix. Correlation matrix is going to be the same. Eigenvalues are going to be the same. Communalities are going to be the same. But our factor matrix now will give you the factor that each one of these items loads on, right? And occasionally you will find something like this. I'll try anything once that loads on 2 different factors. I like to stop and think things over before I do them, which loads on 3 different factors. Oh, am I looking at the unrotated one though? I am looking at the unrotated one. Ugh. The rotated ones, though, still gives you a couple every once in a while. Yes, your pattern matrix, sorry. For the most part, though, this is looking pretty clear, right? We have one item here that seems to load on 2 factors. Yeah, Colleen?
Oh, you can always just finish your thought, or I can ask a question.
No, go ahead.
Okay. This is kind of unrelated. I was just thinking how when we were looking at the scores and we click save as variables,
Oh, yeah.
so then we have all these new variables. Are we, like, is that something we're supposed to look at every time?
No, you don't have to look at them every time.
What's the point of saving them?
The point of saving them is only if you want to know, like, these wind up being a person's latent score on any type of trait, right? And so once you've identified your final kind of factor structure and you've got that score for each one of those factors, you can use those as predictors in regression models or something along those lines, right? They don't have any type of real meaning aside from whether or not you want to use them later on in some sort of analysis. I save them, but it's really irrelevant whether you save them or don't save them.
So it's just so you can go back and decide that people belong to certain groups.
Yeah, I mean, not even certain groups. It's just so that you can find out what a person's kind of general amount is on a given variable, right? So if you, let's say, for example, usually we don't just stop at a factor analysis, right? After you do a factor analysis, after you come up with your latent scores, you want to know how those latent scores are related to something. And so if you had sensation seeking, or you did this factor analysis and you come up with these 5 factors, and then you want to know, like, okay, so how are these things related to alcohol use? Instead of using all 58 of these items to predict alcohol use, you can then use your 5 factor scores, right, to predict alcohol use and say, like, okay, so people who tend to score higher in sensation seeking which is represented by factor score, I mean, FA67 or whatever, right, is related to X. But really, it's just that one individual's level of whatever that factor is. So not necessary unless you want to use it for something more. Yep. All right. So back to our factor score, or I mean our pattern matrix. We have one item that seems to load on two different factors. This item doesn't load the greatest, but it's there. And as we scroll down, what you're looking for is a lot of empty spots, right? Because empty spots are indicating that that item tends to be predominantly associated with that factor. And remember, these spots are only empty because we went in and said, like, if an item doesn't have a factor score of at least 0.3, then we want it to be blank, right? We're going to drop that out. And that's to help us ensure that we're putting our item on the correct factor. We only have a couple, though, that are loading on two factors. This is where things kind of can get more difficult when you have a positive loading one followed by a negative loading one. It's only difficult in so much as this item, if you decide that it should be with this factor versus this factor, then you have to note that this is a reverse coded item, right? And so what you wind up doing is switching coding on some of those things. But, in the video, I think maybe I said this, maybe I didn't. But one of the main problems with factor analysis is that in one population you might come up with one factor structure, and in another population or another sample you could come up with a completely different factor structure, right? And this is a good example of how this might happen. Right now we have one item that seems to load good on, or roughly equally, on two different factors, right? So it's either a problematic item or a problem within the sample. And the original factor structure of this did not have items that were loading across different factors. In something like, who's used the PANAS before, the positive and negative affective scale? Yeah. If you read the way that they designed the PANAS, this is actually really interesting. That there's these two factors, positive affect and negative affect, within the PANAS, right? And are they orthogonal or oblique?
They are related, so they are.
I mean, they're theoretically supposed to be orthogonal, right? They wind up being oblique every time you collect data on them. They wind up being negatively correlated. But the emotion isn't like very discrete. In emotion is not orthogonal, right? The way that they built the PANAS is interesting because they asked a whole bunch of questions. How happy are you? How sad are you? How excited are you? How this, that, and the other, right? And they wound up getting these two factors that look like this with items that were like this, right? All the way around. And no matter how you rotate that, you wind up with some problems, right? And so if you read the way that they built the PANAS, they looked at the highest loading ones here, and then they just dropped these items. They made it orthogonal, right? By saying, like, we're just not even going to ask about this other stuff. I actually hate the way that they made the PANAS. But it does solve this problem, right? You have this thing that winds up loading on two different factors, and you say, like, I don't like that it loads on two different factors. I'm going to dump that item. There are, methodologically, there's, I suppose, nothing wrong with that, but theoretically, there's some concerns there, right? And I suppose if your goal is to get the most kind of discrete, distinct and separate factors that you can, then that's an approach. But it also could mean what? There's something really, I think, important here that we're missing or could be missing if you do something like that.
Efficiency in the construct because you are not putting everything together. You are, for example, in positive effect, you are putting a lot of emotions out just because they do not
Yeah.
possibly.
And so you said, what was the exact statement that you said to start with? I missed.
Efficiency.
You said efficiency. I would use a different word.
Like concept of it.
Validity, yeah. The validity of that factor is maybe questionable, right? Unfortunately, in psychology, nothing is. I mean, like for clinical psychologists, we love having these little pockets that we can just drop folks in, right? Like, oh, you have borderline personality disorder. You have depression. But nobody ever is just depression or just borderline personality disorder, right? In fact, especially with personality, we have started to switch to being able to diagnose personality as kind of along some sort of continuum. But we've done the same thing with substance use disorders, right? So substance use disorders used to be like you have an alcohol use disorder or you don't. And now it's still you have an alcohol use disorder or you don't. But within the context of alcohol use disorders, you might be mild, moderate, severe. Like we have these kind of gradations. We still have, because psychologists still want to have some sort of threshold that we can say once you cross this, it's pathological, and prior to crossing it, it's not. And so I suppose in many respects this is similar. There's another possibility here with this that's going on, and what is this other possibility?
Could it be tapping into something else?
Yeah, there might be another factor that we're just completely missing, right? And we might not have enough items to draw out that factor, and so you have this kind of bleed over of this thing that seems to be pushing to or being pushed by two different factors, but it could be another factor altogether that we just don't have enough kind of traction to find. So unfortunately, this type of factor analysis winds up being very mushy, right? And for math people, for stats people, nobody likes to hear mushy. But it is that way, and you wind up, when you read some of these older factor analysis papers, it's really people making an argument for why this factor structure is like this. And that's why you also, in the past, less so now, but in the past, you've seen a lot of people arguing about alternative factor structures for different things. With the advent of structural equation modeling and the use of confirmatory factor analysis, you no longer have to worry about that as much. Let's go back now. And how would we change this to be a confirmatory analysis? We've got 8 different factors here, right? If we want to have a confirmatory factor analysis, what are we going to do? Okay, so we are going to say that we know that there are only 5 factors, and we only want to specify 5 factors. I'm going to go back in. Descriptives is going to stay the same. Extraction is going to be changed. And we're going to say, no, we know that there are 5 factors, and that's what we're going to roll with. That's the only thing that you need to change for confirmatory versus exploratory. And you hit go. Generally, what you see is within a given sample, and we could do this with this sample, and you will do this for the homework for this sample. You do an exploratory factor analysis on some subgroup of the sample, and a confirmatory factor analysis on the other subgroup. Oftentimes, what happens is people just split your sample in half, right? So you'll randomly, like there's 27 or 2,800 people in here. You might randomly select 1,400 people, do an exploratory factor analysis on those 1,400 people, and then do a confirmatory factor analysis to ensure that you are getting the same number of factors accounting for roughly the same amount of variance. Again, there's no way to test that, right? You're just saying it should be this way. So we rerun this, specifying 5 factors. All of this is, well, it's not quite the same, but it's roughly the same. We're accounting for 46% of the variance, whereas before we were accounting for 56% of the variance. So we're not accounting for quite the same amount because we've reduce this now to 5 factors. Scroll down here. And when you reduce it to 5 factors, you wind up getting a clear pattern matrix, right? Because you've removed those other potential 3 factors, and consequently you wind up finding loadings that are more consistent with just a single factor. I think you might still find 1 or 2 that cross-load. Let's see, maybe not though.
When I feel bad, I will often do things.
You saw one? Where's it at?
There's one at the bottom too. Sometimes there's so many little things.
Pattern should be.
I'm really curious how this ends when I feel bad. So,
Where's when I feel? I think it's when I feel bad. I often make impulsive decisions, or I often do impulsive things. It's a negative urgency construct, and I want to. Sometimes there are so many little things. I don't know what the heck that is, but I often make matters worse because I act. I don't. What is this sentence? I wish I knew. Oh, and now I clicked on it and lost it. Anyway. That might be a rationale for removing this item. I always keep my feelings under control. When we're talking about this scale in particular, I always keep my feelings under control. That sounds very much like a negative urgency type of thing, the opposite of negative urgency, which is I never keep my feelings under control, right? Though this, I'm guessing, is some sort of perseverance or premeditation type of construct. I tend to act without thinking when I am. So this is definitely the positive urgency. So what is positive urgency? Anybody know? Okay, so we'll walk through these 5 kind of things, then we'll look at some of the items real quickly. So positive urgency is when I'm in a really happy or excited mood, I do impulsive things. Negative urgency is when I'm feeling depressed, down, anxious, angry, whatever. I do impulsive things. So it has to do with impulsivity in the context of positive mood versus impulsivity in the context of negative mood. Perseverance is I continue working at something, despite the fact that it's frustrating or what have you. This is a complete aside, but there's actually a researcher, I think in Washington, who did this study to predict success in graduate school. And they had a whole bunch of tasks and a whole bunch of questionnaires. And the thing that they found that was the best, has nothing to do with class. The thing that they found that was the best predictor of success in graduate school was perseverance. And he judged perseverance by taking a block, pulling it out, turning it over and putting it in a new hole, taking a block, pulling, and the amount of time that you'll just sit there and do this meaningless task. I was like, that is the best judge of success in graduate school. How long can I sit there and do a completely meaningless task? Which I thought. I don't know that that's actually perseverance, so to speak, but certainly in grad school you wind up doing a lot of meaningless tasks.
I oftentimes see urgency lumped, or positive and negative lumped together as urgency. So are they then, is that impulsivity in either affective state?
So remember when I said that these things wind up having some kind of higher order structures, and this is why we were often seeing 7 or 8 factors, is because there are these higher order structures. And so I always lump positive and negative together because the correlation between the two. Actually, let's see if we, oh, I need to go back and do this. Analyze, dimension reduction, factor, descriptives. Rotation, is it under rotation? Scores. Does it only, okay. We don't actually get, oh yeah, here's factor score. Oh, this is a covariance matrix. I wanted the correlation matrix. All right, so my guess is 3 and 1 are the 2 urgency ones. Oh wait, maybe it is, nope, because that's 5 and 5. 5 and 2 might be it. All right, let's have a look at these items and see if we can figure out what is positive urgency, negative urgency, etc. And then we can look at the shared variance amongst them. Wrong matrix. Here we go. All right. Let's start with the first item. I have a reserved and cautious attitude towards life. Premeditation, perseverance, positive, negative urgency, or sensation seeking. What do you guys think? Premeditation. Yeah, I have a reserved and cautious attitude towards life. So number 2 is premeditation. Somebody write that down. Premeditation is usually pretty strongly correlated with perseverance. We'll see when we get to perseverance. I have trouble controlling my impulses. That is 1 and 4, so that's not helping us. We'll come back to that. I generally seek new and exciting experiences. That sounds like what? Sensation seeking. Yep, so it's number 3 is sensation seeking. Number 5, I generally like to see things through to the end. That sounds like perseverance. So we would expect 2 and 5 to be strongly correlated. We'll come back to that. Actually, we can actually look at the factor scores to see how strongly correlated those are. When I'm very happy, I can't seem to stay still, I think is what this one is. Positive urgency right there, right? My thinking is usually careful and purposeful. We've already done that. Did we say that we know what 3 is? Yeah, that's sensation seeking. So that means 4, I have trouble resisting my cravings. I have trouble controlling impulses. Neither of those sound particularly negative. When I feel bad, I will often do things. That sounds like negative. Now, interestingly, it also is loading with positive, right? So we said positive urgency is 1, negative urgency is 4, correct? All right, let's come down here. The covariance, this is 1.877. That's the total amount of variance in 1. And its covariance with 4 is 1.529. That's a lot of shared variance, right? If the total covariance is 1.8 and the shared covariance with item 4 is 1.529, that's quite a bit. Let's do this. I've just been adding and adding and adding these. So let's go analyze, correlate, and let's go 1, 2, 3, 4, 5. Okay. And so 1 was what again? Wasn't 1 positive urgency? And 4 was negative urgency, and the correlation between 1 and 4 is 0.65. It's a pretty strong correlation, right? What was perseverance and premeditation? What were the variables for perseverance?
5 and 2.
5 and 2, so we would expect 2 to be very highly correlated with 5, and it is. Those two tend to load on a higher order factor of conscientiousness. The other two load on a higher order factor of urgency, or just kind of rash-based impulsivity. And then what was sensation seeking? What number was that?
3.
It was 3. And so 3 tends to be kind of on its own, and you can see that none of the correlations with 3 are all that high. Statistically significant, but that's because we've got 3,000 people in here. But 0.18, 0.13, 0.17, 0.24 with 5. But for the most part, not ridiculous, right? Now, interestingly, only one of those is negative, and it's with 0.2. And so you actually see sensation seeking being positively correlated with both types of urgency, but also with perseverance. Yeah, and that's also not uncommon. Like, we find that quite frequently, that sensation seeking is positively correlated with it. Sensation seeking, actually, it's interesting, because when you think of conscientiousness, do you think of positive affect or negative affect? Yeah, right? People who are more conscientious tend to have higher levels of positive affect. Sensation seeking, you think of sensation seeking, positive affect or negative affect? positive affect, right? These people, interestingly, like if you look at a correlation between sensation seeking and affect, those people are always happy, right? They're just like they're crazy and they're doing fun stuff, but they're in pretty good moods. And this actually is a complete aside, but kind of forms the basis of our ideas of behavioral activation, right? If you get people doing more stuff, get them active, and sensation seekers are active as hell, then they tend to have higher levels of positive mood as well. And so, not that any of that has anything to do with this, but there you go. So we did today, if we walk through this, we did originally principal components analysis. I have never done a principal components analysis, and I'm not a huge fan of it. And anytime that I ask you to do a factor analysis, please know that you're going to do an actual factor analysis. You won't actually be doing it in SPSS, but now you can if you need to. Next week, we're going to do exploratory factor analysis in M+, and then we're going to do confirmatory factor analysis in M+. And we're going to compare different factor structures. Specifically, we'll compare factor structures. What we often are doing is, does a single factor, because oftentimes one factor accounts for a ton of the variance, right? Does a single factor structure, is it a better fit or a worse fit than a 2 or 3 or 4 factor structure? And we'll talk about this more next week, but you can, we'll be able to say like, okay, so we tested 5 factors and here's what the model fit was. We tested 1 factor and the model fit significantly worse, which is good evidence for 5 factors versus 1, right? We'll also be able to say we tested 6 factors and 6 factors did not fit any better than 5 factors, in which case that's also good evidence for retaining 5 factors, even though 6 might count for significantly more variance. If the model doesn't fit better, then there's no real evidence that 6 factors is better than 5. So, make sense? Yeah.
So if we use maximum likelihood as an extraction method,
Yeah.
I just think it's showing a very better solution than principal access factoring as well,
Yeah.
because there are clear 5 factors in that case.
Yeah, we're gonna save that for next week because M+ always uses maximum likelihood, and so I didn't want to do it today, but you're right. Maximum likelihood will provide you with more clear-cut solutions, and that's why we're going to use M+ moving forward. But and maximum likelihood hasn't been included in factor analysis. Like when I first learned how to do factor analysis in SPSS, we had 2 options, right? Like it was principal components or it was principal access factoring, and now they've included maximum likelihood and a number of other options. But yeah, so next week we're going to use maximum likelihood and we're going to do exploratory and we're going to do confirmatory. But you're right, you do get more clear-cut solutions with maximum likelihood than you do with the others. I mean, that's because it's no longer residual based, right? But it's based on best fit. Like when you think of how maximum likelihood works, right? It's bouncing back and forth until you get to the most feasible solution. And OLS doesn't do that. It's just trying to minimize residual. So, all right, that is it for today, guys. I will get this other video posted. I will get your homework up, and I will go through the homework for next week is going to be do a exploratory factor analysis on this set. What do you get for exploratory? And now using the second set, do a confirmatory factor analysis. And do you get roughly the same amount of variance accounted for, and so on and so forth, right? So, all right, cool. Have a good weekend.